Okay, so totally new topic. This course is a little more topic oriented rather than a progression of one goal like Calc 1 is. So we're going to change gears here from physics and talk about sequences and series. So in order to work on, understand, and get good at sequences and series, you have to know what a sequence and a series is, first and foremost. If you're not confident on just what they are, going any deeper than that doesn't make any sense. Let's start with this. What is a sequence? A sequence is an ordered list of numbers. It's an ordered list of numbers. That's a sequence. Our interest specifically is going to be infinite sequences, right? So an ordered list that just goes on forever. An ordered list that goes on forever. So if the sequence is just the list, then the series is the sum of those values. We're going to sum up all the values in the list. That's the series. If you don't know this confidently, like I said, it makes no sense to talk about all the details of these and learn about these without having this down first. So we'll keep reviewing this. The sequence is the list of values. The series is add them up. Add up all the values in the list. Okay, so the notation for a sequence is we use braces. We often use this like A sub n or B sub, it doesn't have to be A sub n, B sub n. It's the notation for a sequence. So another way to write that then is like this. So A1 is the first value in the sequence. A2 is the second. A3 is the third. So AN is the nth term in the sequence. So the subscript is telling you which value in the list it is. So A11, A sub 11, that's the 11th value in the list, in the sequence. So suppose that our sequence is 1, 3, 5, 7, 9, 11, etc. Then A3 would be 5. And A6 would be 11. Make sure you understand that. So this is A3 is referring to the third value in the list. The third value in the list is 5. What would be the sixth value in the list? So 1, 2, 3, 4, 5. It'd be the next one would be the sixth. And that's 11. Okay, so hopefully you didn't see that. So the question is, can we find a formula in terms of n, a formula that uses n that will give us the nth term? So if you plugged 6 into a formula, it would spit out the number 11. And if you plugged 3 into that formula, with wherever there was an n, it would spit out number 5. So if you saw it before I erased it, don't tell the person next to you. So the goal was try to figure this out, right? So try to figure this out. What's a formula that gives the nth term of the sequence? So like I said, if you saw it, don't just tell the person next to you. So for those who don't know what it is, we want to figure it out. What is a formula that gives the nth value in the sequence? Go. If you're ever not sure when you're trying to do these, this is helpful. Make a table of values. So here I'm making here's the values of n. So 1, 2, 3, 4, 5, what number in the list it is, and then the actual term of the sequence for that value of n. So by looking at these pairs, that could help you try to see the pattern and figure out the formula. So what do we have to do to n to get a sub n? What do we have to do to the number to get the corresponding value in the list? So by looking at these down here, it's easier than looking at the first couple. That's it. Yeah, he's got it up here. So what do you do to 6 to get 11 that you would also do to 7 to get 13? And that you would do to 5 to get 9, that you would do to 8 to get 15. So hopefully a lot of you have got it. You would do it. Multiply by 2, subtract 1. So that this, for the 1, 3, 5, 7, 9 sequence, the formula is 2n minus 1, gives you the nth term of the sequence. Okay, any questions? So remember, a sequence is the list. The series is the sum. We're just going to focus on sequences today and a little bit Wednesday, but then the main focus of the chapter is the series. But you got to know about sequences if you're going to talk about series, because a series is adding up all the terms of the sequence. Yes, sir? No, but n is the term number, right? So yeah, for sequences, n starts at 1, because it's like, which term in the sequence is it? Yeah, so, but that's a good question, because when we get to series, sometimes n will start at 1, sometimes it'll start at 0. But for understanding sequences, it makes sense for n to start at 1, because that's the first term of the sequence, and then n equals 2, etc. But yes, we will see both when we get to series. Other questions? Okay. That's not a great slide. Let's see here. We can still use it. It's not pretty. So we already talked about that. So here's just some examples of more sequences. We already did that. So here's another one. N plus 1 over n. Okay, n plus 1 over n. So then when n is 1, you would get 2. Because it would be 1 plus 1 over 1. Then when n is 2, you get 3 halves. 3 over 2, etc. 4 thirds, 5 fourths. And it would continue like that. Here's another one that's a little more complicated. Negative 1 to the n times 2n plus 1 over n squared. What's that? Yeah, so the second one would be hard. Right. So that first one, if you were given a sequence, it would be reasonable to come up with the formula n plus 1 over n. That would be a fair question. Second one would be harder, right? But still doable, right? Still doable if you worked at it. So what this negative 1 to the n does, what does this negative 1 to the n do? It makes the terms alternate between positive and negative, right? So negative 1, whenever it's raised to an odd power, it's going to give you a negative. Whenever the negative 1 is raised to an even power, it's going to give you positive. So that what makes the sequence, it's called alternate. Alternate between positive and negative values. So this is called an alternating sequence. Okay, so a sequence, so we can talk about sequences being convergent and divergent, and it's really a matter of limits. And what we look at is if the limit sequence is convergent if the limit as n gets very, very large of a sub n equals some finite value L. So what? It's like we keep getting closer and closer to a value L, and then you can choose any amount of closeness that you want, and as long as you go far enough out in the sequence, you'll get that close. And then you can choose it to be even closer, and as long as you go far enough out in the list, you can always get as close as you want to L. That's the idea of the limit, the sequence being convergent. Anything else is called divergent. So the two kind of ways that a sequence can be divergent is if the terms get infinitely large or infinitely large negative. That would be a divergent sequence. Another way a sequence could be divergent is if it just is jumping back and forth, jumping around, and not honing in on a particular value. So the values aren't getting really big or really big negative, but they're not honing in on some particular value, and they're jumping around. Okay, so there's different ways that a sequence can be divergent. So what about a sub n up there? Convergent or divergent? So a sub n, is a sub n convergent or divergent? N plus 1 over n. Well, we look at the limit as n goes to infinity of n plus 1 over n. And when n gets very, very large, does the ratio n plus 1 over n, does it hone in on a particular value? Does it get infinitely close, or as close as we want to a particular value? And if so, what is that value? I heard 0. Does this just decrease to 0, get really, really close to 0? N plus 1 over n. What does it get very close to? 1. Okay, how do I know that? Well, we'll talk in a second. So sequences have similarities to functions. So if we had the function there are some things that are the same and different. We'll talk about in a second. But if I took the limit of this function, x plus 1 over x, and that you did in pre-calculus, you looked at rational functions. Remember in rational functions, how do you determine that limit? You compare if the degrees of the numerator and denominator are the same. Remember, you take the ratio of the leading coefficients. And that was 1. So for finding limits, you can treat these sequences like functions. Okay, but in a second we'll see how they're same and how they're different than functions. Okay, what about the second one? 2n plus 1 over n squared. Convergent or divergent? What do you think? So this is n squared. Does it hone in on a particular value, or does it get really infinitely large negative, or does it just bounce around and not get close to a particular value? Okay, so yes, but it can still hone it still can alternate and hone in on a particular value. Even though it's alternating, it can still hone in on a particular value, even though it's jumping back and forth. So by bouncing back and forth, I meant a not honing in, right? Not getting really close to a particular value. So same thing, thinking about that as a function, 2n plus 1 over n squared, does that converge for large n or not? 2n plus 1 over n squared. When n gets really, really big, do those values get close to a value or not? Okay, it goes back to thinking about this as a function, as a rational function, 2n plus 1 over n squared as a rational function, and our degree of the denominator is bigger than the degree of the numerator. So what's going to happen to that denominator compared to that numerator when n gets very large? How is that n squared going to compare to 2n plus 1 for large values of n? The denominator is going to get much bigger than the numerator. So then that ratio will do what? I hope you're thinking it. 0, right? 0. It's going to alternate, but those alternating values are going to get closer and closer and closer to 0. It's going to go positive, negative, but they're going to get, the values are going to hone in on 0. And so you can choose any small enough value that you want, and as long as n is big enough, you'll get that close to 0. That's the idea of a limit. Okay, so when you're talking about convergence or divergence, we're thinking of these sequences as functions. So how are they the same and different from functions? Any questions on this? This slide here. So how are, let's look at, so suppose a sub n is 1 over n squared. So what function is this comparable to? If I had said, I'll do something original here, say g of x. What function would we compare 1 over n squared to? 1 over x squared, right? Okay, so how are these the same? How are these the same? Well, it's the idea of something of input and output, or an independent variable and a dependent variable. How are they the same? What's a of 11? What am I asking for? I'm asking for the 11th term in the sequence. The 11th term of the sequence would be 1 over 121, right? And that would be similar to saying, what is the value of the function when x is 11? What's the value of the function when x is 11? 1 over 121. So what we're saying here, the conclusion here is that f of c is the same as a sub c, right? Or g, actually in this case g. So the value of the function for when the independent variable is c is the same as the term of the sequence for the c term, right? The cth term. So you have kind of an independent-dependent relationship. That's how sequences are the same as functions. The independent would be like, which number in the list are we? Are we the 5th, the 10th? And that is like the value of our independent variable, the function. And then the actual term value then is the same as the value of the dependent variable. Okay, so let's see. And so we talked about limits, right? So the limit, as n goes to infinity, of a sub n, we can evaluate that limit by looking at the limit as x goes to infinity of g of x. So we can evaluate the limit of the sequence by saying, okay, what's the limit of the associated function? So what is the limit as x approaches infinity of 1 over x squared? We should all be able to know that. That's 0. Therefore, the limit of that sequence is 0. 1 over n squared is also 0. Okay, so what's a difference then? So how is it that the sequence is different from its corresponding function? There's one big difference. How are they different? Yes?
Is it continuous versus?
Right. So when you have a sequence, you have just distinct points, distinct values. This is a discrete kind of function. So if we were to graph that, what would if we put n here on the x-axis, and then a sub n on the y-axis, and we plotted the sequence, what would the sequence look like? What would the graph of the sequence look like? A lot of dots, right? The first dot would be 1 comma what? 1 comma what? 1, right? And then 2 comma 1/4. 2 comma 1/4. The second term of the sequence is 1/4. 3 comma 1/9. So the graph of the sequence would just be points, right? It would just be these discrete points. You only get a point at every whole value of n, right? Because n is the number of the term in the sequence. So 1, 2, 3, 4 would be 1/16, etc. And it would just keep going, right? It would just keep going. What is the graph? What is the domain of g of x? So what are all possible values that we can put into g of x for our input variable x squared? It's not just counting numbers 1, 2, 3, 4, 5, right? What is it? Everything except 0. And so the graph of 1 over x squared So the limit as n approaches infinity or x approaches infinity is the same. It's 0, but their graphs are much different. So g of x is continuous for all real numbers except x equals 0. But the sequence would is just discrete points just at the whole values of n, because n is which number you are in the sequence. Okay, but when x equals 1, 2, 3, 4, 5, you get the same values that you do for the sequence a sub n. But the key here is that we can use the function version to evaluate the limit of the sequence, right? So we've seen that. So by evaluating the limit of the function g, that gives me the limit of the sequence a sub n. Because they both, so that we track the points here, 1, 1/4. So what would happen? All these points would land right on the curve of g of x. And what that function does as a continuous function is exactly what those points will do, get very close to 0, and the limit will be 0. So the sequence is basically a subset of the function values, right? The sequence is a subset of the function values for whole number, or the counting numbers of the independent variable. Okay, so let's look at some common forms of sequences. So the first one is one over n to the r. So r is some positive value. These are all examples of 1 over n to the r. Okay, so when do these converge? For what? So the question is, for what value of r? So for what values of r does 1 over n to the r converge? So r can be greater than 0 to be this type of sequence, but now we're saying for which values of r greater than 0 give us a convergent sequence. Give us a convergent sequence. So anyone have any ideas about that? So r greater than 1. R greater than 1. So let's look at let's look at some graphs of that to kind of check that hypothesis for r greater than 1. So we're going to look at graphs of function. What function are we going to look at that would be corresponding to this sequence 1 over n to the, say, 1 over n to the 1, or 1 over n to the 4, or 1 over n to the half? What function would we be interested in? Say f of x equals, what would the corresponding function be to 1 over n to the r? He wants 1 over x to the r. Agree with that? Do you agree with that? 1 over x to the r would be the function associated with the sequence 1 over n to the r. Okay, I hope it's right. We'll go with it. So I'll use capital R because little r is used for something else in this program. So then, so what will we get when r equals 1? So what function will we get when r equals 1? Can you sketch it without a technology? Do you know what that function is? So we're thinking about the sequence 1 over n to the 1 by investigating this function 1 over x to the 1. What will it look like without technology? Can you sketch that? I'm going to do 1 over x to the 1. Should all be able to sketch that without technology. Okay, draw it with your finger in the air. Okay, but we're only interested with, so here's 1 over x to the 1. We're only interested in the sequence, so that would be like the discrete points starting at x equals 1, right? So we're thinking about now the sequence. Does it converge? Does 1 over x converge for large values of x? If x gets, yeah, it converges to 0, right? It converges to 0. And so similarly, 1 over n to the 1 converges. Okay, let's try. So what about if r is something greater? Is it going to converge? And to what? So if it makes something greater than 1. 5. Will it converge? And if so, to what? Yes, to 0, right? Just do it a lot faster, right? So now 1 over x to the 5th is going to get, we talked about this principle before, so now we're talking about the same thing, but discretely, it's going to get to 0 a lot faster because that denominator is getting a lot bigger, a lot quicker. Okay, so then what about something less than 1? So, for instance, 1 over the square root of x. And r would be what for the square root of x? 1 over the square root of x. What would r be? 1/2. Can you sketch 1 over square root of x without technology? Could you sketch that without technology? What does it look like? Is it an increasing or decreasing function? How about that? Is it increasing or decreasing? As x gets big, does this get smaller or larger? 1 over radical x. Smaller, right? So for large values of x, your denominator is going to still get larger and larger, even though you're taking the square root of it. You're still going to get a larger and larger denominator, meaning the ratio is going to get smaller and smaller. So this will be a decreasing function. Does the limit exist? Let's zoom out on the x-axis. So I'm going to show more and more of the x-axis. Convergent or divergent? Is this flattening out for some value? So is it getting closer and closer to some value? Yeah, I mean it's basically the same as 1 over x. You know, for any, so if you had 1 over a million, well now you would just need a million squared, and you'd have the same 1 over the square root of a million squared. You'd get down to the same x value. So again, however low of a value you want, you just need x big enough, and you can get there. So this goes to 0. The limit is 0. 0.1. So this is 1 over x to the 1/10. It's just going to go, it's still going to approach 0, just really, really, really slow. So here we are at the, what is 9? Is that million or billion? Billion, right? So Even when you get to 1 billion, you're still, this is 1 over x to the 1/10 now. Anyway, what's the point? The point is that what does r need to be for this to approach 0? We're only at 1 billion, right? We've got infinity to go, right? We can make numbers a whole lot bigger than this, and then much bigger than that, and then we keep getting larger and larger. And so even if you have a small, this 0.1, this exponent is very small, there's no limit to the size of x that you can make it. That thing is going to, the limit is going to be 0. Okay, so what does r need to be for 1 over n to the r to converge? Yeah, greater than 0. So our first type of sequence, 1 over n to the r, the limit as n goes to infinity of 1 over n to the r equals 0 if, as long as r is greater than 0. Okay, another kind. P to the n. P to the n. So now what? N is the exponent. Okay? Here n is the exponent. When would this have a chance of converging? So what kind of exponents would make this get really large versus maybe have a chance of getting this to converge? So what are we talking about? Like some number to the so what are examples of this? 3 to the n. Negative 2 to the n. 1/2 to the n. 1 to the n. So here's all examples of these. 3 to the n, negative 2 to the n, 1/2 to the n, 1 to the n. So imagine, n is going to be 1, and then n is going to be 2, and then n is going to be 3, and you're going to get a list of values for each one of these. So let's make this list. So write out, let's do these two. It's time to go. So if you were to write out the list, 3 to the n would be what? 3 to the 1, 3 to the squared, 3 cubed, 3 to the 4th. That would be that sequence, 3 to the n. Convergent or divergent? Convergent or divergent sequence? Divergent. This is going to get really big, right? And just keep getting as big as you want. 1/2 to the n. 1/2. 1/4. 1/8. 1/16. That will converge to 0. So this gives us a clue as to what P needs to be, what the base needs to be for these sequences in order to get convergent. So when that base is outside of 1 or negative 1, it's going to diverge, get really, really large. But when you're within 1 to negative 1, then your terms, you keep multiplying by another fraction, and so your terms are going to get small and go to 0. So let me just write that down. I'll be done. So it'll be 0 if you're between 1 and negative 1. Why? Because it's like you're multiplying by the same fraction over and over again. 1/3 times 1/3 times 1/3 again times 1/3. That's going to approach 0 if your p is between negative 1 and 1. There's a special case. It'll converge to 1 if p equals 1. Why? Because what's your sequence? 1, 1, 1, 1, 1, 1, 1, right? No matter how many times you raise 1 to the first power, to a power, you just get 1. Any other values, this thing diverges. So divergent otherwise. So greater than 1, less than negative 1. Okay. So I'm going to post